In these videos, we're going to study polynomial functions. So what's a polynomial function? Well, we've already seen one. Our quadratic was actually a type of polynomial function. Here's like my general form for this, and I know that looks pretty complicated, but these a's are just real numbers, and these are x to some powers. Okay, so for example, a polynomial we've already looked at would be like 2x squared minus 3x plus 1. That's called a quadratic polynomial, special case, because we can do a lot with these because we have some formulas that allow us to find the vertex and the zeros, and they look like parabolas. But once this number gets bigger, these things are a little more complex. And an example of this would be 4x to the 5th minus 3x to the 4th plus, and it doesn't have to descend by 1 the power. You could just have 2x minus 1. That fits our definition. This would be a 5th degree polynomial. Okay, so that's what we're going to do. So let's take a look at an example. This is a relationship between unemployment and inflation. So you can see there's as unemployment increases, you can see inflation decreases. As unemployment increases, there's less spending, right? There's less demand. It puts downward pressure on wages and prices. So if I were to plot these, what I want to do is, this is my first example of regression so far in this course, and we're going to do a lot more of this because it's actually an easy way to apply the concepts we're learning in this class to like some real world situation. For example, if I were to plot these guys, I get this graph. Okay, so this is the same data set here plotted on the XY plane, and say, well, I can see the downward trend. So the question would be, what kind of function is that? Desmos is a great tool for this, and I'll show you specifically how to use this for a regression later. You can kind of follow along what I'm doing here. You just have to call the y's and the x's by using x sub 1 and y sub 1, and the tilde is an approximation of the data set, okay, with a function. So anyway, we'll do more on that later. Right now I just want to come up with a function. So I'm going to say, let's try a quadratic function. A x1 squared plus b x1 plus c. So that's our typical quadratic, and Desmos will just fit it to the data. And we look and say, oh, that's not a bad fit. I mean, it's going through the points pretty well, so I'm modeling it with this function. And here are the coefficients given. It'd be 0.04x squared minus 1.35x plus 9.8. It's not bad, but then you can see, well, it might work within the scope of the data, but then I don't think this is really going to happen. It's going to start increasing again. So what I could try is a cubic. So let's say ax cubed, this is a polynomial, right? And then my next term would be squared. And my third term would be x to the first power, and then I'd have a constant term. Okay, and that's a pretty good fit as well. So I can see that if I were to write this function down, the a coefficient would be negative 0.003, b would be 0.1, c would be negative 0.17, and d would be 10, the y-intercept there. Okay, so this is an application of a polynomial. It's a cubic polynomial. All right, so we'll come back to that. We'll do a lot more regression. Regression's pretty interesting. I can actually find actual functions that model my data. All right, so we'll do a lot more of that moving forward. But let's jump back right now and just see if we understand polynomials. So this is a polynomial, factored. This is not. Oh, this is a polynomial. This is there to throw you off. It threw me off. That's still a real coefficient. So officially, it's a polynomial based on the powers of x being integers, positive integers. Let's go back to that definition. As long as the coefficients are real, the leading coefficient highest. So basically it's written in this form, and I should add to that, where is it? N has to be an integer that is non-negative. So N, these values here the exponents would have to be what we call whole numbers. Sorry, not whole numbers. I want to do, whole numbers. That is 0, 1, 2, 3, 4. What set is that? That's the non-negative integers the whole numbers. Okay, so yes, 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 and no, not a polynomial, because that power, if I rewrote it, would be 2 fourths times x to the negative 2, and that's not a non-negative integer. It's negative. Okay, polynomial that has degree 0 is a constant function. Constant. That would be, and this one's kind of weird if I had like 4x to the 0, that's my function. Officially, that satisfies my condition for polynomial. X to the 0 is 1, so that's just 4. So a constant function is considered a polynomial. Degree 1, that would be something like f of x equals 2x plus 1, right? Degree 1, so that's a linear function. And we studied this guy last unit, quadratic. Okay, end behavior is important. I'm going to skip right to the graph of this. If I have a odd function and the leading term is positive, it's always going to do this at the end. And this is how we write end behavior. As x goes to infinity, as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. If the leading coefficient is negative, it just flips that upside down. We'll look at some examples here in a minute. If it's a positive and the leading power is even, that is an even degree polynomial, it's going to do what your quadratic would do, right? If you remember from quadratics, f of x equals x squared goes like that. F of x equals negative x squared goes like that. Okay, but the end behavior will be the same. As x goes to infinity, y goes to positive infinity. As x goes to negative infinity, y also goes to positive infinity. But there might be some other things. The reason there's like a big gap here is because we're not sure what's happening in here. We're going to learn this later. It could be doing something like this, and we'll figure that out later. Okay, but right now we're just focused on the end behavior. What happens as x goes to infinity and negative infinity? Okay, so we can just remember that. Here's my first example to determine the end behavior. How do I answer that? I can always say as x goes to infinity, y goes where? That's my answer. As x goes to negative infinity, y goes where? This is my answer. And because I have an even polynomial, leading term negative, if I were to draw a picture, it does this and this, right? That's this case right here. And then I just decide how to answer my question. Well, if it's going down, as x goes positive, y goes to negative infinity. And same thing back here, as x goes back, y goes to negative infinity. Okay, here's a quadratic. Determine the end behavior. This would be the same as the previous one. That is, as x goes to infinity, y goes to negative infinity. Even though it's not a 4, it's still even, and that's negative. So as x goes backwards, as x gets small, y goes down. In this case, though, in reality, the height cannot go below the ground, so we do have a application here. So if we can review our domain for this function, quick review. We'd studied these functions. This is quadratic, right? A little review of quadratic. We would say, oh, what's the domain of that? And we did a bunch of these before, so I won't find the answer to this one in the video. I'll just set it up, and you can find out when that guy hits 0. That would be the end of your domain. It would be from 0 to whatever the solution to this equation is, the positive solution. Okay. So before we dive into these things, we're going to need to learn how to divide. So we'll cover that in the next video.